Question 12, Part C. The region enclosed by the semicircle y equals the square root of 1 minus x squared and the x-axis is to be divided into two pieces by the line x equals h, where h is greater than or equal to 0 and less than 1. The two pieces are rotated about the x-axis to form solids of revolution. The value of h is chosen so that the volumes of the solids are in the ratio 2 to 1. Part 1. Show that h satisfies the equation 3h cubed minus 9h plus 2 equals 0. Since the rotation is about the x-axis, the volume V is given by the formula V equals pi times the integral of y squared dx, where y is equal to the square root of 1 minus x squared. Now the graph of y equals the square root of 1 minus x squared is a positive semicircle of radius 1, and when that's rotated about the x-axis, that'll form a sphere of radius 1 unit. And we'll need to know the volume of that sphere. We'll get to that shortly. But firstly, we need y squared. We're given y. So in order to get y squared, we need to square both sides of this equation. And we get y squared is equal to 1 minus x squared. Now we know that a sphere is going to be formed. The radius of that sphere will be 1 unit. And the volume of that sphere will be 4 pi over 3 cubic units. And that comes from the formula 4 pi r cubed over 3, where the radius r is equal to 1. Now a ratio of 2 to 1 implies division of the volume such that 1/3 of the sphere's volume is between 1 and h. Now I've sketched a diagram here to indicate this. Here's our positive semicircle. It's going to be rotated about the x-axis. Now that semicircle is from x equals -1 to x equals 1. Here's our h. And h is positioned such that 2/3 of the volume is to the left of h and 1/3 of the volume is to the right of h. I'm going to consider this volume here, just to avoid using the negative in the integration. Just makes it a little bit easier. So pi times the integral of 1 minus x squared dx from x equals h to x equals 1 is equal to 1 over 3 times 4 pi over 3. In other words, we're getting 1/3 of the volume here, which is equal to 1/3 of the volume of a sphere of radius 1 unit. And that's what we found up here. Now we can divide both sides by pi, and just with a little bit of simplification on the right hand side, we get the integral of 1 minus x squared dx from x equals h to x equals 1 equals 4 over 9. So move the page up a little bit. There we go. Okay, performing the integration, we get x minus x cubed over 3 from x equals h to x equals 1 equals 4 over 9. Applying the limits of integration, we get 1 minus 1 over 3 in brackets minus h cubed over 3 in brackets. It's very important to use the brackets here, especially since we have a negative here and a negative here. And that equals 4 over 9. So with a little bit of simplification of this equation, we get 2 over 3 minus h plus h cubed over 3 is equal to 4 over 9. And simplifying further, we can collect some like terms. We've got 2 over 3 here, 4 over 9 here. We can move that 2/3 over to the other side, becomes negative 2 over 3. We get negative h plus h cubed over 3 is equal to negative 2 over 9. And if we multiply all terms by the denominator 9, we get negative 9h plus 3h cubed equals negative 2. And moving the negative 2 over to the left-hand side, we get 3h cubed minus 9h plus 2 equals 0 as required. Part 2. Given h1 equals 0 as the first approximation for h, use one application of Newton's method to find a second approximation for h. Newton's method is based on finding the equation of the tangent to the curve that corresponds to our first approximation, and then interpreting the x-intercept of that tangent as our second approximation. So the function that we're going to define is y equals 3h cubed minus 9h plus 2, which is sketched here. Now, in order to find the equation of the tangent, we need the gradient of the tangent, but to get the gradient of the tangent, we need the gradient function, y dash, which is 9h squared minus 9. Also, we need the value of the function where h is equal to 0 in order to use the point gradient formula, and we're going to need that a little bit later on. So at h equals 0, which corresponds to our first approximation, y is equal to 2, and y dash is equal to negative 9. And we get that by substituting 0 for h here and here to get our value of y. Now this corresponds to the y-intercept of the function as well. Now y dash is equal to negative 9 when h is equal to 0, and that's how we get our y dash is equal to negative 9. And this corresponds to the gradient of the tangent at the point 0, 2. Now the h variable is our independent variable, which is equivalent to our x coordinate. So using the point gradient formula, and noting that h2, which is our second approximation, has a y coordinate of 0, we're going to solve for h2 the equation negative 2 equals negative 9 times h2 minus 0 in brackets. Now, expanding the brackets on the right-hand side, we get negative 2 is equal to negative 9 times h2. Dividing both sides of the equation by negative 9, we get h2 is equal to 2 over 9. So that'll be somewhere here. Now, this diagram is not drawn to scale, but it's certainly closer to the 0 of the function than our first approximation. Therefore, the second approximation for h is h2 is equal to 2 over 9.